Can you hear me? I hope you can.
Okay, so let's continue with the next talk. Next speaker is Martin Benning from the University of Cambridge. So for him, quite local talk, very nice. So he will talk about nonlinear eigenanalysis, and I think that's also very related to deep learning in a certain aspect.
So thank you very much, Christoph, and thank you very much to the organizers for having me here. Yes, I'm going to talk about nonlinear eigenanalysis of variational regularisation operators, which is a joint work with actually many invaluable co-authors, where I thought I'd rather actually depict them on one slide, which sort of include Joanna Gra, who did actually most of the work, PhD student here in Corolla, obviously. Also Guy Gilboa and his student Ross Nosek from the Technion, Martin Burger and Daniel Kremers. So an outline of this talk is they're first going to talk about nonlinear eigenanalysis of variational regularisation operators, where I'm first going to say what I mean in the context of variational regularisation, and then try to move on towards a more learning-based approach that involves nonlinear eigenproblems, and then conclude with a few applications and some outlook. So, first part, I want to sort of introduce what I mean when saying variational regularisation. I mean, to this audience, usually that's not really necessary, although we have seen that there are different views on how to define regularisation. I mean, we have seen Ozan's take on inverse problem from a statistical point of view, and I'm going to follow up on a more deterministic point of view, which could also be extended to a statistical inverse problem. So the obvious introductory slide, what is an inverse problem when you're working inverse problems, is basically to show that you try to recover some unknown quantity U dagger from given measurement data f via some operator equation, k of U dagger equals f, where k is some operator mapping between, in this talk, between a Banach space and some Hilbert space. We have some data which, when you write it like this, somehow implicitly has to be in the range of k, and you have some unknown solution to the inverse problem. Obviously, the data is usually not in the range of the operator, so we only have some sort of approximate solution, and the data is rather in some Hilbert space and contains numerous sort of sources of errors. And therefore, we have to somehow determine what is the error and how do we measure it. And as I said, this is more the deterministic view, a deterministic take on inverse problems. So we assume that we have some sort of data fidelity function, which is proper, lower semi-continuous, and that the data that we have is, when we plug it into this data fidelity model, is bounded by some error delta. So you could obviously also go ahead and say you draw several instances and then take the expected value, and it has to be delta. But we stick to this deterministic framework. If you stick to such a data fidelity model, then also it makes more sense not to follow up on just looking at what's the range of an operator, but rather what is an effective range, by saying, okay, what are the data? What is the data that we have in some Hilbert space, such that the argmin of my data fidelity is, and with my inverse model, my forward model, is not empty. And then usually we also, in most cases, we have the scenario that we have inverse problems where we have, and we have seen this also in the previous talk, where we have lots of explanations for instance, measured data or different data points where we have to pick a particular one, and this usually comes from some form of prior knowledge, and therefore we have to somehow we have to have some form of selection operator, where at the basis of this we have some proper lower semi-continuous and convex function j that's been parameterized in terms of some parameter, often just a scalar, and then not necessary, but in the context of learning also by some other operators or transforms, such that when we have a solution of this optimization problem with data in the effective range, that we pick the one that has that basically sets this value here to some minimal value. And here A simply denotes the space of parameters which can be arbitrary. And to just have an example that this sort of unifies classical regularisation theory is that when you have a linear unbounded operator and your data error is given in terms of the squared Hilbert space norm, and your regularize or your space in which you look for the solution is also given, is also a Hilbert space, then you can just basically look for the minimal norm solutions and choose your functional j to be a squared 2 norm with some parameter alpha that has to be larger than 0. And then all these definitions basically reduce to the classical error analysis where you look for a bound of your noisy data and your noise-free data, and the effective range just becomes the normal range, and the selection operator just selects the minimal norm solution. And all these definitions, they in some way already intuitively gave rise to how to define a variational regularization model. When you have this data fidelity term and you have this regularisation functional, or this functional that incorporates your prior knowledge, and basically adding them together and minimizing sort of the sum of these for some given data f delta and some parameters alpha means that this sort of arcmin is a potentially set-valued operator where the input is really your noisy data f delta alpha, and you want the output to be, or an element of the output, you want it to be sort of close to your unknown true solution u dagger. And obviously, again, when you go to this classic scenario where you have linear bounded operators and you have L2 spaces, choose this quadratic regularisation function and the quadratic data term, then this is nothing else than rewriting your classical Tischendorf regularization as an operator. And so what we're interested in, and I'm also going to say in a moment why we're interested in it, is to now study solutions of this variational regularization operator in terms of looking at eigenproblems. So what are functions that, when are being plugged into the forward model, you can recover with the variational regularization model with some bias, some loss of contrast, which is usually given as the eigenvalue. So, and there's lots of work, and so just as a quite broad overview slide on works on eigenanalysis and singular analysis, usually in nonlinear. So the linear case, there are classical works by Stewart and obviously the Engel-Hanke-Neubauer book of singular vector decomposition in the inverse problems context, but there's a lot of work on PDEs on nonlinear eigenproblems to study solutions of PDEs, but also in control analysis and, for instance, in our interest also in image processing. There are many words usually or often sort of being seen as originating from this seminal work by Mayer on this total variation eigenfunctions, with lots of works by Sales and Chom and Antonin is also here. And then also in machine learning, interest has been drawn for eigenvalue problems, usually by solving certain types of graph cut problems, and then in the variational regularization we try to build a few foundations for a more general formulation of what is an eigenvalue problem for these kinds of operators. So what do I mean? I have already said it in terms of words. When I look for eigenfunctions, I basically look for functions that are part of the solution of this regularization operator. So if this operator is not multi-valued, then you can just think of an equality here. So you plug in a function into your forward model, plug it into the regularization, and you would like to get it back with a particular value lambda. And so why? So because it allows us to understand what are sort of typical solutions that we can recover perfectly with a regularization method, and also this eigenvalue somehow quantifies this bias, systematic bias, and may tell us a little bit about systematic biases of a particular method. And so if we now look at our variational regularization problem and simply formulate the optimality condition, given that given that J is convex, we basically look for the derivative of f with respect to the first argument a k star in front of it, and then the model, so the assumption plugged in that u lambda is basically, so that the solution is lambda times u lambda. We are also now, and for the rest, assume that k is a linear unbounded operator, and that our data is given as k of u lambda. Then this is sort of the optimality condition, and we now make some further assumptions to simplify this problem so that we can actually really derive some explicit eigenvalues and eigenfunctions. So we assume that our data is no longer quite general, quite arbitrary, but we rather say it can be written as some function g of the difference of these. So it's not something like a Kullback-Leibler entropy or whatsoever, but it could be any kind of norm, semi-norm, norm squared, where we have sort of this difference, where then this whole expression here changes, that we have the Frechet derivative of g, and here we can put these together, the ku lambda and the lambda times ku lambda, to just have lambda minus 1 times ku lambda, also assuming that g is continuously differentiable and convex, and more importantly also that it is somehow, that the derivative is somehow homogeneous in some way, so that we can find a function that when we have a constant inside, that we can pull out this constant, which is, for instance, true when you think about g just to be the square 2 norm. This is just the identity. And we have this actually on the next slide as an example. And then we can plug this out, or we can pull this out. And the same we assume also for the subdifferential of j, because otherwise we can't really study much, that we can also pull out sort of a constant and the regularisation parameter for now out of the functional. So obviously very restrictive, but in order to look at certain examples, we have to boil it down first. And then we can rewrite this eigenvalue problem of the regularisation operator as this sort of eigenvalue inclusion in this subdifferential of j. And to give an example, so if g is simply the square 2 norm, as I said, S1 is just the identity. The regularisation functional, for instance, is the square 2 norm with some parameter alpha. It's also the identity multiplied by alpha, and we get sort of this eigenvalue problem of the operator k star k, or the singular vector decomposition problem of the operator k. But we can also make this a bit more, we can make this quite different by saying we have a square 2 norm, and for instance something like the 1 norm is a regularisation functional, and then this function S2 is something like alpha times the sine, not something, it is actually alpha times the sine of x, so that when we plug out a constant, the constant kind of vanishes. We just basically change the sign, and then this whole expression here reads as 1 minus lambda over alpha times k star. Ku lambda has to be in the subdifferential of the 1 norm at position u lambda. So we get also an eigenvalue problem, but an eigenvalue inclusion that can be written like this. And so, seeing this obvious analogy to singular vectors, because we basically ended up with eigenvalue problems, or generalization of eigenvalue problems of k star k, we want to define the sort of generalized notion of singular vectors, where we say we have two vectors or two functions. It's not vectors, it's just called singular vector. Two functions, u sigma and v sigma, and some scalar sigma, and we say they're supposed to satisfy, so this first condition is quite classical in singular value theory, if ku sigma equals sigma times v sigma. But the second condition is generalized, so where we have this dual singular vector function, and we have k star g prime of v sigma is supposed to be in the subdifferential of j of sigma times u sigma. If g is just the 2 norm, the square 2 norm, then this is, and j is also just the square 2 norm, then this is exactly the dual singular vector condition of k star v sigma equals sigma times u sigma. So it generalizes, but it is a bit more general compared to this. And I want to give an example for a function that is a generalized singular vector and not in the classical sense. where we look at the total variation as a regularisation function, or a total variation with Dirichlet zero homogeneous boundary conditions. And unfortunately, because I couldn't actually compute it otherwise analytically, I've chosen K to be the identity operator, which is usually a bad choice in inverse problems because it's not a compact operator. But it's also easier than to actually see what's going on. What you can then show, in order to satisfy this condition here, for J being this total variation and K being the identity, and I'm sorry, I forgot to write this actually, and G being just the square 2 norm, then Haar wavelets are eigenfunctions of this total variation. So you have a natural link between Haar wavelets in 1D, not in 2D, or in, well, then it depends on the norm that you choose for the vector. But in 1D you have this natural connection between Haar wavelets and total variation, that Haar wavelets are eigenfunctions, or sorry, singular vectors of the total variation. And so one is the U sigma, and the other is just a scaled version of the V sigma. And when you have, for instance, such singular vectors, then you can now go ahead and determine what your loss of contrast is, or your eigenvalue lambda of your reconstruction problem, by just going and plugging in this pair of dual single vectors, the V as your data and the U sigma as your solution. And in order to come to this definition of singular vector, and that also explains why we define it this way, is that we now, so when we start from here, we now rewrite U sigma in terms of, or K of U sigma in terms of V sigma, which gives us another sigma here. So we have sigma lambda minus 1 times V sigma. And here we simply divide by sigma and then plug out a sigma. And now we use the same trick as before, that we pull out these coefficients. And so we have now something that looks almost exactly like the singular vector condition, but with this additional factor here. And so we now basically can determine, or can decide that in order to, we have to now choose lambda such that this particular constant is exactly 1. And then we have already guaranteed that this condition is satisfied. And so what that means is we basically have to choose lambda such that they are equal. And then we can already say that lambda times U sigma is in the subdifferential of R of V sigma for the parameter alpha. And if we go and have examples again, because it always makes everything more clear, if we go to the classical 2-norm case, where we have the functions basically just being the identity functions, we end up with the typical Tikhonov loss of contrast. So exactly, I mean, in the classical inverse problem sense, regularisations are derived, or in the deterministic sense, are derived from singular vector decomposition theory. And this is usually what you get for, in terms of your Tikhonov regularisation, as the coefficient in your Tikhonov regularisation. However, if you now do this for this 1-norm example, or for any one homogeneous regularisation function, also such as the total variation, you get a different loss of contrast, which is 1 minus alpha over sigma. But the nice thing is they're both consistent. I mean, this is exactly what we have in the 2-norm case. But also the second part is consistent with classical singular value theory, also apart from the fact that it's more general, that when alpha goes to 0, we exactly converge to 1 over sigma, which would be sort of the optimal way of recovering a singular vector. However, what we also see from both of these eigenvalues that you have for your regularisation problem, they will both never be 1 if alpha is not 0. And therefore it means we have a systematic bias when we try to recover something. So we never get back our true signal. And therefore I want to now talk a little bit about bias correction, which has already been discussed yesterday by Christoph in terms of the, well, in a more general way, which I will come to later in terms of the spectral decompositions. But it all starts with iterative variational regularisation, and we also have seen this morning in the talk that where Bregman iterations have actually been used in the context of denoising, we now use them in the context of inverse problems to see that we can actually correct for the systematic bias by going away from simple variational regularisation by solving a sequence of variational regularisation problems. And in this case, the only thing we replace in our regularisation operator is that we don't have this regularisation functional here anymore, but we replace it with the generalized Bregman distance. We pick an iterate of our as a solution of our regularisation operator, and then we update the subgradient in the same way as it has been described in the morning, and we stop this iteration scheme when our data error is below sort of the data error that we expect for our data in terms of a noise level. And the Bregman distance is nothing else than the difference of the functional j at the value uk, in this case, minus its linearization around the point uk minus 1. So that's in the moment all that you need to know about Bregman distances. And when you change your model in this particular way, then you can do this eigenanalysis, and you can now prove that you overcome this systematic bias. So what we have shown on an earlier slide is that sort of our eigenvalue problem when J is 1 homogeneous or the subdifferential is zero homogeneous, that we get this solution to eigenvalue problem for a singular vector, for a pair of singular vectors. And we can actually compute the exact same thing for this iterative regularisation scheme, only that then we have now these iterations, and depending on how alpha is chosen, we first have 0 solutions until we reach some index k star, and then we have this same loss of contrast, but instead of having a 1 here, we have the k star here. And then we can easily compute, I'm not doing this, but I'm just showing it, that with the next iterate, the k star plus 1, we get rid of this loss of contrast, but rather have 1 over sigma. So we don't have 1 over sigma or 1 minus alpha or something over sigma. We have exactly 1 over sigma, so we get this back perfectly. And therefore we correct for the bias, and this is it's really a simple computation. And also, in case this doesn't convince you, I also have a numerical example, which is part of the appendix of this talk, where you can actually compute that when you have a realistic problem and you compare Bregman iterations or linear variational regularisation, iterative variational regularisation with just variational regularisation, that you systematically improve over the bias, but with sort of the same variance within your data. Therefore, it outperforms variational regularisation. And it also builds the basis to now look at a generalized spectral decomposition, and this is what Christoph was talking about yesterday in the context of segmentation, and here in the context of inverse problems, that you can now make a very trivial observation. You can write every solution of your iterative variational regularisation scheme simply as the sum over the differences of two solutions of your previous iterates, and just sum them up. If you evaluate the sum, you exactly end up with u0 minus un. So therefore, this is a simple way of rewriting it. And we can define these as functions phi k, and then sort of write it as a sum over some phi k, and also equip the sum with some coefficients in order to emphasize different phi k's. And the question now is, why is this meaningful? And also I want to mention that this is based on the nonlinear spectral total variation transform that Guy Gilboa first came up, and in this form it's mostly based on the version presented in this paper by Martin Burger. The reason is why does this make sense? Because I could take other differences here than just the simple differences, but we have seen this yesterday by Christoph, and now we can actually also support this with some analytical computations, that eigenfunctions of our regularisation operator will actually be localized within the spectrum. That means when I have a pair, like a singular function again, and in this case I rescaled my solution, so I didn't plug in v sigma in here, but k of u sigma. So the solution here is k star minus alpha times sigma, but this is exactly what we had on the previous slide. Yeah, when I usually compute this with one singular vector, then my solution will be 0 up to the index k star, then I will get this, and then I will get u sigma for all indices after k star. So if I then take the difference of these solutions, most of the time this will be 0, apart from the indices k star and k star plus 1, where it will be either this version with a loss of contrast or minus this loss of contrast. So in order to just show this graphically, when we have, for instance, example again of a Haar wavelet, and we have a Haar wavelet with a particular scale, which shows alpha fixed to some parameter, then we can analytically compute that at the index k star being 10, that we sort of then get this particular loss of contrast, which is somewhere at the range of 0.1, and then we get at the index 11 the same thing with 0.9. And everywhere else this is 0. And if we now have different scale here, so a different Haar wavelet with, for instance, a larger scale, then they will appear in the spectrum at a different position. Also what we have seen yesterday, numerical observations by what Crystal has shown. And therefore, what we could now do when we have both in our signal, we can separate them again by suppressing or enhancing the particular parts of the spectrum. And here, to give a more concrete example of some real data set, is this image of a B, or this spectral decomposition of a B. And since it's a B, it also can be called a spectral decomposition of this image, where you clearly see that these spectral components really represent features at different scale. And here, the underlying basis is, again, we have the squared 2-norm data term, we have the total variation as a regularisation function, we have the identity operator, and you clearly see that you have, because of the total variation, you don't have sort of scales that are global, but you have really discontinuous edges, but then you get smaller and smaller features the further you progress. So, and all these components added up give you back your B. And now you can do exactly what I just described, but with real data. For instance, taking this painting of the Mona Lisa, where you have all these scratches. When you take a picture of the painting, you see all these fine structures and scratches. And you can now say, okay, I take all the indices up to, all the coefficients up to some index. So I take all the spectral components up to some index k star. This is like a low-pass filter. And then I receive this image here. Or I take all the indices up from that index k star, and then I get this high frequency component. And the question now is, what is it useful for? And we have actually seen yesterday that you can tackle really important problems like cancer with such a problem, like cancer detection. We have decided we basically just have some fun with it. So we don't do anything useful. We basically just do something silly with it. And you can create memes, for instance. You could imagine that you have a picture of Donald Trump, and he has this conversation with Abraham Lincoln where he says, like, hey, Abe, I know how to make your memorial great again. And his vision of how to make his memorial great again is probably something like this. That you have now the Trump memorial, and you can also imagine that Abraham Lincoln's response is something like this, maybe. And more, not to actually give any political opinions here, or maybe to some extent, but you could also have a different example. I simply show this because it's a bit more impressive in terms of the features that you can extract, where Hillary Clinton may think like, okay, I'm definitely going to win this. Not even the American people would consider playing the Trump card, and then she sort of ages badly afterwards, feels terrified, as we all do, and this old lady laughs a little bit about it. And simply, this is more impressive because we really transferred the features of this old lady onto Hillary Clinton. And just to say, since we're in England here, you could obviously replace Hillary Clinton with David Cameron and replace Trump with Brexit, and you could actually create the same meme. So how did we do this? It's a pipeline of different processes, but at the core of this is really just the spectral decomposition. Where, so first, basically, we detect phases, we align landmarks to a landmark-based registration, so that you really align these phases, you do segmentation, that you don't fuse everything that you don't want to fuse, but just the parts of the phases. But at the core is exactly the spectral decomposition that I just showed to you, where for this example, for instance, in order to create this Obama-Reagan fusion, again, no political motives behind it, simply because Ronald Reagan has actually quite distinct wrinkles. And so what we have done here is we have taken the low frequencies of the Barack Obama image, some of the medium frequencies of the Ronald Reagan image, and some of the high frequencies of both to create sort of this particular image. So yeah, this is also what you can do with these kinds of methods. And now you may already wonder, so what does this all have to do with learning? I mean, this is all now more like an eigenanalysis for variational regularisation methods and extensions. So therefore, I want to take a step back now and go to discuss some sort of other potential problems that we work on, but that also are related to nonlinear eigenproblems. And so we have seen lots of impressive works and ideas. What I'm going to show you is actually very basic and rudimentary, no sort of sophisticated architectures yet, but I hope you still get the idea from why we do this and what we're doing. So I want to go back, and basically back to the era of dictionary learning, if you wish. I want to present a very simple learning problem where you have some proper lower semi-continuous convex function, J. You have some training data given as some matrix, where, for instance, the columns are all your instances of training data, and then you have some linear transformation that you would like to know that makes this whole expression here very small. But if you don't constrain it, the simple trivial solution would just be 0. So therefore, you constrain it, for instance, to have Frobenius norm equal to 1, or with some other constraints. And yeah, goal is to to make this minimal. And this problem can also simply be seen as some eigenvalue, nonlinear eigenvalue problem, where, so first of all, you could write this as a quotient because this is simply 1. And then you can take the derivative of this quotient, or the subdifferential you can compute, and you basically, again, end up with an inclusion. So the only thing that's missing here is some operator k on this side because it vanished. It's in the subdifferential of this expression here, and the sigma can also be evaluated when this is normalized. It's just 1 over the evaluation of your functional j. So solving such a problem, again, mounts in solving nonlinear eigenproblems. And to go even a step further and simpler, let's assume that we have just one set of training functions, and we have a sparsity-promoting function, j, in this case just the 1 norm, and we simplify our operator in order to reduce parameters to just look at convolutions. Then the whole model simplifies to minimizing the convolution of h with some function u plus, subject to this normalization here. And an example, for instance, could be, and this is a bit unfortunate, so there is actually a color gradient between these two, so the image stops, but it now looks all white. If we, for instance, think about we have such a geometric structure, and we want to now find a filter that makes this very small, for instance, in order to use this functional as some form of classifier, then this is sort of the optimal filter that we would get. And this actually makes total sense, because if you look at the filter, if you take pixel differences here, like as you have given here, and then take the exact reverse pixel differences here, and then add them together, this will be 0. So we find a kernel, a convolution kernel, such that this function u plus is actually in the kernel of the operator that we have learned. So in that sense, great, we have found like a global minimum. because we end up with 0. And then we could use such a filter to for instance solve variational problems, in this case like a Morozov regularisation problem with this particular regularizer, where we have where we take this new filter that we have learned and then we can denoise it. And because when our image has sort of the same structure, or maybe thinner stripes or slightly bigger stripes, but definitely stripes in, or maybe also stripes in different orientation, as we're going to see in a bit, then we can perfectly recover this simply because this is in the null space. And for elements in the null space, your reconstructions will be best, because that basically means that you have an eigenfunction to your operator with eigenvalue 0. Sorry, the eigenvalue for the regularization operator is 1, but the singular value is 0. This is basically what it means, and therefore you get perfect recovery, and you can also compute this. However, we want to look at the second example, where we just basically rotated this whole image by 90 degrees, and we get sort of the same optimal filter, which is also natural, because again, this is in the null space of your operator k. And okay, maybe you get some translations of it because it's a non-convex problem and there are some invariances, so you may not get exactly the same filter, but the filter does the same thing. And the pro is that you now have two filters, or two functions, or two images that you can individually, for instance, denoise with this previous method perfectly with the same model. But on the other hand, you could also ask the question, have we actually now not learned something that's too general, or have we learned anything about the structure? Could we differentiate between these two? No, we couldn't, because when we apply the filter to both signals, they're both 0. So therefore, we can't differentiate between the two. And for that reason, I want to modify this first model that we have shown in terms of some quotient minimization, which is based on two papers that we have presented over the last year, where we now go ahead and say, okay, we have some positive training data as before, but we also have some misfit training data, some negative training data, and we now aim at minimizing a quotient. So basically changing our nonlinear eigenvalue problem, but changing the Rayleigh quotient to something different, saying like we have the same function here and we want that this gets really small, but we want this at the same time to get really big. So that we can, for instance, differentiate between them with our regularization model. And if we go back to the same example, the simple example with these geometric structures, we have again these stripes here in the horizontal direction and in the vertical direction, or the other way around. And we now plug 1 in as the u plus, so we again have our simple model with the convolution, just one data each, plug this into the denominator, and what we then get is a different filter. Obviously we can't get the same filter because otherwise the whole thing would blow up. Now we really get like a difference, or finite difference scheme into one direction with one orientation. And if you now, for instance, plug together, like take a combination of these two images and try to use the Morozov regularization again to denoise it, or to regularize it, then what you also see is that this right-hand side here is being much more severely affected as the left-hand side. So exactly what we were hoping for. We wanted something that is really particularly good to this signal, but really bad to this signal. So, and in the difference, the absolute difference to the ground truth, you see that there is much more loss of contrast and blurring going on this side than on this side. And you can do this with other geometric structures. Obviously, due to our simplicity, due to the simplicity of the model, we are limited to simple examples, so we can't plug in any deep neural network architectures yet. But if we, for instance, have these stripe structures, then we get this kind of filter. And again, we see, I mean, it's difficult to see on this projector. It still looks pretty good, but it's more blurry, more fuzzy than on this side, less sharp. And here, you can clearly see it in this difference image. And we have more examples, but I kind of have to hurry up. One comment to how do we solve something like this numerically, because this is quite a challenging question. It's a non-convex problem, but the observation is again that it is basically a nonlinear eigenvalue problem, and that you can solve it with methods that have originally been adapted for classical eigenvalue problems, such as the inverse power method, and then in 2010 Hein and Bühler have adapted this method to something more general that can handle functions like this, or also by Xavier Bresson and others, and there has been sort of the extension of this model that is more stable because it adds like a quadratic to it, because the previous model has definitely some flaws in terms of existence of minimizers, and we can then basically solve a sequence of variational problems where we linearize the non-convex part, we update the eigenvalue, pick a subgradient, and then normalize the solution, and this is also guaranteed to converge. And there are also some alternatives now to compute eigenfunctions, which are, for instance, given in this paper here by Ras and Guy recently. So to conclude and show you some applications, so what could we, for instance, use this for? I want to start with some regularisation model, some informal regularisation model, because one idea that then came immediately to our minds is, what if we have signals that where we really know they are additive compositions of different structures? Can we now use such a model to decompose these structures again? Which would mean that we would look at this informal convolution model, for instance, having a data fit here and looking for a function that consists additively of two functions, such that we have two filters that we learn prior to this process, h plus and h minus, and there should be a tilde on both of these filters, and we pre-compute these filters with exactly the routine that I just showed, where we, for instance, for this example, again, use u plus and u minus as these geometric structures, but then we reverse their roles for the second filter, so that we have one filter that acts really well on this and really poorly on this one, and the other way around. And if we do this and have, like in this case, obviously it's a very simplistic model, but we just add them together, and then we have this sort of checkerboard model with linear decay, then we can actually decompose this up to some numerical errors into these two components again. And this also works to a large extent with noise, which I didn't include. And here with the other test image, although these stripes are slightly different in thickness as before, and then we get these diagonal filters, and again we can kind of take this image and decompose it into two components, where the only errors that we observe here happen at the boundaries because we don't have the correct boundary condition for a model. And another sort of application that this can be applied to as an idea is classification. I guess we have seen this now so many times that I don't have to explain this anymore. The MNIST problem, which is also, as we have seen and known, is a very simple learning problem. We make it even simpler. We don't handle the whole classification problem. We just say we take two digits that we want to differentiate between with our simplistic model. So this is really being on the playground and having very simplistic toys, where we now compare our two initial approaches. So the one being the approach of having just minimizing the one norm model under this normalization, and the second approach being the approach of learning two filters with sort of positive training data. So here we take two digits, 3 and 0, and we take all the images that belong of the training data that belong to the digit 0, and we plug them into the numerator, and we plug all the other ones in the denominator, and then we reverse this by having the 3's in the numerator and the 0's in the denominator, and we learn these filters. And then what we do is we want to use them, we basically evaluate them both together with the one norm, and want to take the minimal value as an indication of which class it belongs to. And the filters that we get are, in the one case, basically some sort of finite difference approach here, which some favorable orientation here and some other orientation there, but they look quite similar. Whereas with this quotient minimization, the more complicated model, they look actually quite different. Seem to have captured more structure or difference about these models. And then also, if you do this very naive classification result, which in no way competes with anything that's state of the art, especially when you just have two classes. You get this 78% success rate with these types of functions, so they can discriminate to some extent, but not very well. And if you have the same number of parameters, but this different model approach, then you get a jump to sort of 95% by not having increased anything in terms of parameters, but just by training them differently. And you can also, this is something that's still ongoing work, so therefore I can't really show you this. The open question is still how do we extend this sensibly to all the 10 classes, which the naive approach is that we basically do the same strategy for all these filters, but our limitation that we still have is that we still have to make these filters more different to each other, that we have lots of cross sort of identifications that shouldn't be there. And but in general, this is sort of the next step to see if we can actually come up with more sophisticated problems where you can apply this strategy to, and to basically do the same thing but on a different data set. Joanna has also looked at this on the reflectance and texture database by the Columbia Utrecht universities on images, and just looked at two classes, grass and wood texture, and can we differentiate between them with these model, and the result is between these two classes we can. For more classes we still have to put in more work to make this work. With this I'd like to finish. So what we have seen? We have seen that nonlinear eigenanalysis is actually useful in understanding, at least from a mathematical, analytical point of view, what a regularisation function is doing, or operator is doing. And we also have seen that iterative regularisation can outperform, or at least in terms of bias, outperform variational regularisation, and that this part can be extended to the spectral decomposition, which can be used to maybe cure cancer at some point or to create funny memes, so see what you prefer. And that quotient minimization, another form of nonlinear eigenproblem, allows to incorporate misfit information into a training process instead of just having fit training data. And yeah, as an outlook, obviously we would like to look at more sophisticated models, have multiple classes for the fit and misfit training data, which at the moment doesn't work so well. And something that has just been pointed out recently, which we definitely want to explore, is that there seems to be a resemblance to adversarial networks, which, well, for a fixed eigenvalue, if you wish, or not a variable parameter, looks quite similar to the kind of optimization problem that we then end up with in the end. So definitely something we want to explore. And with this, I'd like to thank you for your attention, and I'm happy to take your questions.
Oh yeah, not too much time, but
yeah,
maybe
lunch.
one or two
Lunch
questions make up Kate before we have the lunch. So.
Everyone wants lunch.
Yes. Okay, so I think the lunch we have enough time to discuss further. So thank you very much, Martin.
Welcome. Thank you.